Hey, today we're going to delve into related rates. This is going to be a great application for things like the chain rule and even implicit differentiation when we look at it, okay? Um, so another important use of the chain rule is to find the rates of change of two or more related variables that are changing with respect to time, okay? For example, when water is drained out of a conical tank, the volume, radius, and height of the water level are all functions of time. These variables are related by this equation, that the volume is 1/3 times pi times the radius squared times the height, if you remember that from geometry. And what we can do is differentiate this equation with respect to time to achieve a related rate equation. Okay. And that's just them taking the derivative with respect to t and finding that. And again, we can see that the rate of change v is related to rates of change h and r, okay? So we're going to need to know those different pieces. So we can see it's like we talked about with implicit differentiation, it's important to see what variable we're differentiating in respect to, because otherwise we wouldn't have had those rates of change pop up. So we'll start with just kind of a simple example. In example one, we're going to suppose both x and y are differentiable functions of t and that they are related by the equation y equals x squared plus 3. So what we're going to do is we're going to start by differentiating each side with respect to t, because they said they want us to find dy dt given that x equals 1 and that dx dt equals 2. So that means that we can find the derivative with respect to t of our original equation, which was y equals x squared plus 3, okay? So again, we're going to take the derivative with respect to t of both of those sides, okay? So here, this just becomes dy dt. And then here, this becomes 2x dx dt, and then the constant's just 0. Okay. Well, remember, it gave us some information. It told us that x equals 1 and that dx dt was going to be 2. So now we're going to use that information. Now we're going to use that x equals 1 and that dx dt equals 2. So that means that dy dt is going to be 2. And then in for x, we can put 1. And in for dx dt, we can put 2. And we can see that, therefore, dy dt is going to be 4. So even if we end up with another rate of change, if we know the value, we can then still find it to find the derivative of y with respect to t. So in this example, we were given an equation that relates the variables x and y, but we are going to be looking, the point of these related rates is for us to develop the equation ourselves. So we're going to have to create a mathematical model from a verbal description. So let's try that in this example 2, okay? Well, let me maybe, okay. A pebble is dropped into a pond, causing ripples in the form of concentric circles, okay? The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Okay, so the first thing that we're going to do, and I have these guidelines for solving related rates down here, I'm actually going to call this step 0. I know I'm changing my mind. Step 0 is where we're going to make a sketch, if possible, because I don't think you always can, labeling the quantities, okay? And so in this example, in example 2, we're just dropping a pebble into a pond. So here's step 0. and we're getting circles. Oops. And it's talking about the radius r of the outer ripple, and that is increasing. So I'm just going to, I don't know, maybe draw it like this and call this r. Okay. I mean, the step 0 sometimes is hard for me, I'm not going to lie. Okay. All right. So that's the first thing we're going to do. The next thing, and I'm going to combine this into a step 1. Okay. Oops, you can't see that. Is that in your step 1, we are going to organize our information. And we're going to organize the information very specifically. We're going to identify all given quantities, so everything that we're being told that we know, and we're going to look at the quantities to be determined, like what we want to find. At that point, I also am going to include in that step for then us to write an equation involving the variables that we can use. So that's kind of our step 1, is to organize our information. Okay. So again, step 0 is to draw a pic if possible. Okay. And then step 2 is going to be to organize our information. I often like to, the reason I combine those into one is I sometimes like to look at the equation that we're dealing with. So when we're looking, it's looking at the total area, right? So for an equation, we can use the area, and this is a circle that we drew. So we can say that our equation is that the area equals pi r squared that we can use, right? Then we want to look at a given rate that we have. Okay. The given rate we see is that the radius of the outer ripple is increasing at a constant rate of 1 feet per second. So the radius is changing. That's going to be dr dt. That's what that's telling us. And it tells us that it's 1 foot per second. So that's the given rate. So we look at an equation with the given information. We have the given rate. And now we're going to look at what we're supposed to find. Again, this wants us to find the rate that the area of the water is changing. So this wants us to find dA dt. And specifically, notice that they refer to finding that when the radius is 4. Okay. So all of this is what we're going to be doing in what I renamed as step 1. So you're going to organize your information. Okay. And the things that we want to include in the organization of the information, and you can do it in any order, like whatever you find it, but we're going to look for a specific equation. They usually give us some sort of a given rate. And then let's look at what we are supposed to find. Okay, so that's step 1, to organize our information. Okay. Now, step 2, which was step 4, that now I'm calling step 2 so that it doesn't seem like so many steps, is to implicitly differentiate both sides of the equation with respect to time. But this is important here. We're going to write this as well. Do not substitute known values into the equation prior to differentiating. We have to wait until after step 2 to do that. So up here, we'll write that in step 2, that we are going to differentiate, okay, with respect to t. But when we do that, I'm going to put this little beware up here. Okay, that you can, it's so tempting, but you can't. You cannot do immediate substitution on any variable that could change. And in this situation, the radius can change, the area can change. Like, it's so important. You can't put, so even though I have this 1 foot per second, or this, or the fact, in this case, the fact that r equals 4, I cannot put that into the equation, because then I would just be differentiating a equals 16 pi. That's not going to make any difference, right? Okay, so you have to wait. So let's differentiate. And so we're going to differentiate this specific equation, all right? So the equation that we had was a equals pi r squared. So we are going to differentiate with respect to t, okay? And then let's see what we end up with what we've learned about implicit differentiation. So here this just becomes dA dt. And then this is a constant. Remember, pi is a constant, so we can pull the constant out. And now we want to differentiate r squared with respect to t. So that's going to be 2r and then dr dt. Okay. So then, you know me, I'm going to make it look a little bit nicer. So I'm going to rewrite that as 2 pi r dr dt. Okay. So that's step 2, to differentiate with respect to t. Okay. So step 0, draw a pic if possible. Step 1, just organize all the information in the problem. Step 2, differentiate, but don't put any numbers in, essentially, okay? So now we're going to go on to step 3, which is printed here as step 5. So step 3, now at this point, after completing step 4, now you can substitute the variables in that you know, all right, with the specific rate of change or the variables, okay? So again, step 3 is going to be to evaluate. And these are the two things that we're going to use to evaluate, part of the information that we had in our organization of the info. So here we're going to evaluate when r is 4 feet. Oh, I should have put feet up there. And the dr dt is 1 foot per second. Sorry. Okay. So let's put that in there. We've got that the derivative of a with respect to time is going to be 2 pi and then r, which is 4 feet, and dr dt, which is 1 foot per second. And so therefore we can see that that's going to give us 8 pi, feet times feet is feet squared per second. And that is the rate at which the area is changing when the radius is 4 feet, okay? Cool, right? And of course you could do this with other information as well. So this is like a general rule for the derivative of, well, I guess for the rate at which the area is changing. But notice that it's going to vary dependent on what r is and what your rate of change of r is as well. Okay. So example 3, let's try another one. Find the rate of change of the distance between the origin and a moving point on the graph of y equals x squared plus 1 if dx dt equals 2 centimeters per second. And this one wants it in terms of x only. So I'm going to do a little sketch. Okay, so step 0, it gives us this graph. So I guess I'll just draw that for our graph. Y equals x squared plus 1 means our vertex is going to be at 0, 1, and it just looks like this. And it does want the distance between that moving like that point and the origin. So essentially, like, we could put any point on here, and it's like from here to the origin, you know, how far away that is. Okay. Again, step 0, I don't really love, not gonna lie. Anyway, so let's do step 1 because that's a nice thing for us to do. Step 1 is something we should always do, always organize that information. So what they're talking about in this question is the rate of change of the distance. This isn't a distance. Distance formula is something that we could do. So let's think about that for our equation for the distance. Or that for our equation is that idea of the distance. So we could do the distance between the origin, which is 0, 0, and a moving point on the graph. So let's think about what the moving point on the graph would be. Notice that x is going to change, and the y value is going to be x squared plus 1. So that's what we're looking for, the distance between the origin and a point on the graph, which can be defined as x squared plus 1. So let's use our distance formula. We could have x minus 0 squared plus x squared plus 1 minus 0 squared. Again, I know I'm being dramatic. So that's like x squared plus 1 squared. Let's flesh that out. If I square x squared plus 1, that's x to the 4th plus 2x squared plus 1. So I end up getting x to the 4th plus 3x squared plus 1, and that's my distance, okay? So notice in the first, well, in example 2, the equation was pretty cut and dry. In example 3, we kind of had to do a little work, okay? But there's our equation. Now let's look at the given quantities. So what is our given rate? Okay. The given rate that we have in this question, notice, is this dx dt equals 2 centimeters per second. So that's handy. That's our rate of change. And what it wants us to find is it wants us to find the rate of change of the distance, right, between the origin and the moving point. So if we want to find the rate of change of the distance, that means that we want dd dt, the change in distance over time. So that's step 1 for us to organize that information. And I know in number 2 we had a specific point, but notice we have a moving point right now, so it's not at a specific point. So I don't know if you want to put like at any x, okay? So, but they don't give us a specific point to use. Okay, so now let's do step 2. And step 2 is when we differentiate. So that means we're going to have, so step 2 is when we're going to have the derivative with respect to time of this equation that we came up with. Remember, and that was d equals the square root of x to the 4th plus 3x squared plus 1. Okay? So we want to differentiate that with respect to t. All right? All right, so let's go to work. You guys agree that this is like the same to the 1/2? I probably should have written it that way. But on this side, we're going to end up with the derivative of d with respect to t, so d dt. And then if I want to take the derivative of this, we're going to have to use chain rule, right? So this whole thing is our inside function. And then we have u to the 1/2 is our outside function. So we're going to have 1/2 times x to the fourth plus 3x squared plus 1 to the negative 1/2, but then we still need the derivative with respect to t of the inside function, x to the fourth plus 3x squared plus 1. Okay, so again, using chain rule again. So I'll leave this alone, and so that I can focus on taking the derivative with respect to t here. So all of this is going to be with the dx dt essentially. So like this would be 4x cubed dx dt, that would be 6x dx dt. So because, like, just to kind of save some steps, because each of those is going to have the dx dt, instead of writing it and then factoring it out, I'll just kind of leave it like that. Okay. And so then I could just rewrite this a little more nicely. 2 is going to be in my denominator, as is the square root of x to the fourth plus 3x squared plus 1. And then in the numerator, I can have this 4x cubed plus 6x dx dt. Okay. Oh, look, here we go again. And then we've got 3 terms involved that are all even. So the derivative of the distance with respect to time, then I could write as 2x cubed plus 3x all over the square root of x to the fourth plus 3x squared plus 1 dx dt. Okay, so that's our step 2. Okay, so all of the stuff that we've been talking about this whole time, we can apply in that step 2. Okay. And now in step 3, we essentially are just going to put in this 2 centimeters per second. It was at any x value, so we're just going to take, this 2x cubed plus 3x over the square root of x to the fourth plus 3x squared plus 1. And then we essentially just put in dx dt, which is 2. And then that's really it for this one. This one isn't as exciting. So then I could say that this is 4x cubed plus 6x over the square root of x to the fourth plus 3x squared plus 1. Okay, so this is at any x value. So what that means is that now you could, because it's in regards to x, is that you could find it for any x value now that you've done all that work. Okay. Those are the steps. Okay, let's maybe do a couple more just to kind of get you in the groove. Okay. The only thing I'm going to say up here, as far as this place where it says some examples of rates of change, and I think just doing some problems is the best way to do that. But sometimes, for me, when I don't know what's going on, which is often, that units can be very helpful when you're determining the given rate. Okay, so just know that sometimes it can be really helpful for us to figure out what that's going to imply later on. All right. So in example 4, this one says that air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Okay. So again, like, I don't like step 0, but step 0 is to draw a picture here is my picture of this balloon. Okay, I don't know what else you want me to do. All right, so there's a picture of the balloon that's actually a sphere. Unlike these, see, these aren't really spheres. Spheres like, like a perfect, like global. Anyway, so that's step 0. Let's go on to step 1, which I think is really a little more important. So step 1 is going to be to organize the information. So what I mean by that is that if it's talking about air being pumped into a balloon and then the rate is 4.5 cubic inches per minute, the fact that they're talking about cubic inches per minute means that they're dealing with volume, right? And when you think about the logistics of the problem, that does make sense that if we're pumping air into something that we're talking about the volume. So why don't we try that? That our equation is going to be the volume. And do you guys remember the volume of a sphere? No. So the volume of a sphere is 4/3 pi r cubed. That's how we find the equation for the volume of a sphere. Okay. Remember, we also want the given rate. And that's usually pretty obvious, that this is the rate of 4.5 cubic inches per minute. And again, that cubic inches means a volume. So that tells us that the given rate is dV dt. And we'll just write that that's 4.5 cubic inches per minute. And then it's asking us to find the rate of change of the radius. So the rate of change of the radius is going to be dr dt. And then specifically, it's going to be when r equals 2 inches. Now remember, we're not going to use r equals 2 until the very end, all right? But we can still just make note of that in our organization step, okay? So now step 2 is that we are going to differentiate with respect to t. We had that the volume is 4/3 pi r cubed. And so we're going to differentiate with respect to t. So that means that here I've got dV dt. Remember, 4/3 pi is a constant. And then we can differentiate r cubed with respect to t. So that's going to be 3r squared and then dr dt. Okay. Let's simplify. Oh, that's nice. These can cancel. And so that means that dV dt is going to be 4 pi r squared dr dt. Okay. By the way, I about lost it back in the 90s when I realized the relationship between like the volume of a sphere and the surface area of a sphere. Like, okay, anyway. So now that we've differentiated, let's go on to step 3. And step 3 is where we're going to put the different pieces in. We know that dV dt is going to be 4.5, and now we're allowed to put in that r is 2. So in for dV dt, we can put 4.5 equals, and now I have 4 pi, and then in for r, I can put 2, okay? So essentially, I'm just putting everything in. So in for 4.5 is going in for dV dt, 2 is going in for r, and now I can start simplifying from here. So I've got 4.5 equals 2 squared is 4 times 4 is 16 pi dr dt. So that means that we've got 4.5 over 16 pi equals dr dt. Now, it's best practice to not have a decimal in your final answer if they want it exact. So can't we just multiply by 2 to get rid of the half? Essentially, isn't that 4.5? So I'm going to write my dr dt, if I want it exact, as 9. So I have to multiply by 2 over 2. So 9 over 32 pi. Not 932 times pi, but 9 all over 32 pi. And in this case, the radius would be changing in inches per minute. And that would be my dr dt, which is the rate of change of the radius, specifically when the radius is 2 inches. You could put that in the calculator, and say, if you did that, I think it's 0.09 inches per minute. But I just wanted to speak with you about how you would simplify that fraction. Okay. One interesting to note that in this example, notice that the volume, it says it was increasing at a constant rate, but our radius was increasing at a variable rate. So like notice to find our radius, that is going to be dependent on the rate of change of the volume and the radius itself. So just because two rates are related doesn't mean that they are proportional. Again, in this case, the radius is growing more slowly as the time increases. So let's maybe try one more example for today. And here's example 5. It says an airplane is 6 miles high, flying on a path that will take it directly over a radar station. If the distance from the plane to the radar is decreasing at a rate of 400 miles per hour, when the distance is 10 miles, what is the speed of the plane? Okay. So in this question, you have, and they've kind of modeled it here. I'm just going to pretend it wasn't there because they never seem to give me pictures when I need them. So here's the ground, okay? And then you have this airplane that's 6 miles high, okay? So that's 6 miles, okay? And here we have a plane that's flying, okay? And it's flying on a path. We're assuming that it's not going to crash, that it's going to go straight, that it's going to take it directly over a radar station, okay? So here's the radar station. So it is going to keep flying, and then it's going to end up directly over the radar station. It says if the distance from the plane to the radar is decreasing at a rate of 400 miles per hour, when the distance is 10 miles, what is the speed of the plane? And notice that they've named that for us. They've named that S, probably because they know I don't like using S in equations. You could call it D if you wanted. Anyway, but that's what we're doing here, is that's going to be called S. And as far as an equation to use, and sometimes it's a little easier for us to see, like to write the other information out. So maybe it's not clear what equation we're going to use. That sometimes happens, all right? So maybe we could even just look at the given rate. It says here that the distance from the plane to the radar is decreasing at a rate of 400 miles per hour. Well, this S was the distance from the plane to the radar. That was S. So it says that that is decreasing at a rate of 400 miles per hour. So that's how this is changing. So that must be ds dt. And it's decreasing, so that's going to be negative 400 miles per hour. Okay. As far as what we're going to find, it wants the speed of the plane. So what could we think of as the speed of the plane? Notice that's not going to be this. The plane isn't flying here. The speed of the plane is going to be what's happening while we go this way. Remember that the speed of the plane is going to be the derivative of the distance that the plane is traveling, which means that it's going to be basically like the ground speed. Okay, so we can maybe call that x. And again, the speed of the plane is going to be the ground speed. And so we can call that maybe dx dt. Again, remember that velocity speed is the derivative of a specific distance. And so again, we're just going to think about the ground speed, which could be the derivative of this specific distance x. So what we want to do is find dx dt, and specifically when the distance is 10 miles. So when our distance x is 10 miles. All right, so now that we have this picture, is there any formula that pops out in your head that we might be able to help us use with all this information? Well, maybe you see that we have a right triangle that's here, right? If the plane is 6 miles above. And one thing that we can do if we have three sides of a triangle is we can use the Pythagorean theorem, that s squared equals x squared plus 6 squared. So that's something, again, that maybe I wouldn't have thought of that at first. But after I investigate the problem and I put the pieces in the puzzle, this is where the picture I think is important, then I was able to figure out, okay, let's do the Pythagorean theorem to help us out. So I can simplify that into s squared equals x squared plus 36 maybe, okay? And that's, again, my step one. I don't know if it's helpful to label how we're doing this, okay? So now let's go on to step two. And step two is where we're going to take the equation s squared equals x squared plus 36, and we're going to differentiate it, of course, with respect to t. All right. So when that happens, this ends up with 2s ds dt, and then this will end up being 2x dx dt plus 0. And again, we're finding dx dt, so I'll divide by 2x. So I have 2s over 2x ds dt equals dx dt. Say that 8 times fast. So therefore, what we could say is that dx dt, we could say is s over x ds dt, okay? So that's what we're getting for step two. Now, in step three, we want to put these different pieces in, right? So in step three, we know that ds dt is negative 400 miles per hour. Can I not write the rate, like the unit? Okay. I also know that x equals 10. So if I started to put that in, I have dx dt equals s over x times this negative 400. So I'm just putting that in. So, oh shoot, you guys, I did this whole thing wrong. Sorry, the dx dt is when the distance is 10 miles per hour. So it's when s is 10, my b. Okay, so when the distance from the plane to the radar is 10. Oh, geez, oh, Pete. So this is when s is 10. I'm like, wait a minute, my picture isn't looking right. All right. So, sorry, it's been a long day when I'm doing this recording. Anyway, so what we've got is we have the information for s, the distance from the plane to the radar. We've got the rate of change, but we don't have what x is, all right? So notice that we need x too. So, but what is x, since it's not 10, like I had told you for the last 5 minutes, okay? How can we find what x is? Well, this is specifically when s is 10. So what we can do is we can use the equation with S equals 10 to help find X, since it's now legal. Okay, remember before we differentiated, we said it was illegal to find anything because we might put it in. But now that we've differentiated, now it's kind of safe for us to do that. So let's try to find that. Let's do S squared, so 10 squared equals X squared plus 36. So I think you guys can tell what this is going to be. We can see that X squared is going to be 64 and X has to be 8. We can tell that it can't be -8 because it's that idea of the distance. So now we can put this into the dx dt formula that we had figured out. So we can say that dx dt is going to be 10/8 times -400. And if you compute that, we end up with dx dt being -500 miles per hour. That is our velocity. However, when we are talking about speed, remember that speed is the absolute value of our velocity. So what we would need to do for speed is just ignore the sign. And we would just say that the speed is 500 miles per hour. Okay, so the velocity is the direction. And again, because the plane is approaching the radar, that that distance x is decreasing, right? So essentially, because the distance is getting closer, that's why the velocity is negative, but the speed itself is the absolute value, which would be the 500 miles per hour, okay? Whew, that's a lot, especially when I mess up like that. So thank you for being gracious, and I'm glad we fixed that. And that's a little bit about related rates. So see how you do, and we'll do some more practice next time.